before the video starts, I just want to discuss the problems that we cover. So here is a separable. Then we do a exact. We do exact with a integration factor needed. And then we do a basic linear equation. Then we do a Bernoulli equation. Here's a homogeneous and a higher order homogeneous equation. Then we do we use method of undetermined coefficients, and we also use the variation parameters for this problem just to show that both of them work. And then we do, well, this one is actually in a different video. This is a really longer problem, so it'll be in a different video on my channel. And then lastly, we do a Laplace delta Dirac problem. So this kind of covers everything for Laplaces that you need to know, basics. And what I recommend is I will have the link of the blank version of this, so with just the problems and everything in there. And I recommend you try to do the problems beforehand, and yeah, and then you could watch the video to see where you need help on and things like that. So I'll link everything, all the sheets, all my Laplace stuff here, I'll link it to. Everything will be linked, everything you need, and the video will start in about 2 seconds. Okay, so we're going to start this video off with the separable equation. Damn it. Yeah. Separable is usually the first method you learn. So, okay, first off, we can already see that this is dy dx, and that this is a function purely of x, and this is a function purely of y. So what we can do is see this is dy dx, split the differentials, put dx over here, then grab this guy and put it under here. So we'll have dy divided by e to the negative y and x plus 2 dx. dy e to the negative y is equal to x plus 2 dx. So that's what we have. And then, we could see that e to the negative y under something is e to the y dy. So now everything looks a little bit nicer. And what we can do is we can integrate, right? So if we're going to integrate both sides, e to the y dy is equal to the integration of x plus 2 dx. And then we could see that we're going to get e to the y, right? And we're also going to get, that is also equal to the integration of x squared plus 2 plus 2x plus some constant c. I like to add the constant to the side of x because I want y explicitly by itself. But before I do that, why don't I find what that c is? Maybe make my life a little bit easier right now to find what that c is. So applying initial conditions where y and x are going to both be 0. That's what this is telling me. So I'll have e to the 0 is equal to 0 plus c. And we can see that c is equal to 1. So now I can rewrite this as e to the y is equal to x squared over 2 plus 2x plus 1. And I'm going to put this whole side right here as one big number. So that will be x squared plus 4x plus 2 all divided by 2. Now, just tell you guys why I'm going to do that. That way, if I want to get rid of this e to the y, I can take ln e to the y, and this just becomes y, and then I could take ln of x squared plus 4x plus 2 divided by 2. And I think this looks like a lot nicer of an answer. And we could just box our final answer right here. There we go. Okay. Now we got a differential equation, and well, I know because the way I got the problem, it tells me it's exact. So we're going to use the exact method, but realistically there may be another way to solve this equation, but we're going to use the exact method. Now, since I can only ever see the exact method in the form df dx dx plus df dy dy, since I can only for myself see it in this form, I will put this into this general form because I need to do it for myself just to see it. Okay, so there's a y prime here. So what I'm going to do is go 3x plus 2y, and then I'll have dy dx here, right? And then plus 2x plus 3y is equal to 0. But what I'm going to do is, oh damn it, what I'm going to do is multiply everything by dx, so dx dx. But then this part over here, I'm going to erase this for a second, times dx is equal to 0. So if I want to make this look even a little bit more closely like my form, I'll write it right below. We'll have 0 is equal to 2x plus 3y dx plus 3x plus 2y dy. Now the reason why I did that is just because I like it in this form. Okay, now using the exact method, we usually call this df dx. We call m, and then what we do is we take m with respect to y, and we call this df dy, and this is equal to n. And then when you take n with respect to x, if these two are equal, then it's exact, and then we can go about it. Okay, so let's check that. So m with respect to y, this is m with respect to y. I mean, this is m, and we're going to take it with respect to y. So this is a constant, this will be 0, and then this will just be 3. So it's 3. And I'm saying, if we take this, and we take this with respect to x, it will be 3. And look, it is. Okay, which is n with respect to x. So it's exact. So since I said this whole thing of m df dx, we can kind of use this relationship, right? So if m is equal to df dx, this is like a little formula for a separable differential. So then we could write it as df is equal to m dx, right? And we can integrate both sides, and then we get f is equal to m dx. Integrate it. All right. So this is what we can do, and we're going to do that exactly. So, by the way, you could pick either side. Just pick this side right now because it's like the easiest one. It's also equally as easy on the right-hand side too. Okay, so f is equal to what? The integration of 2x plus 3y dy dx, my bad. And then we can see that this will be x squared plus 3yx and plus, so we usually write plus c, but since we're integrating with respect to x of a multivariable function, our constant is going to be some function y. So we'll write it g of y. Okay, so we have f, but we don't know what g of y is. So we can find g of y by taking f's derivative, because we know what f's derivative is with respect to y. We know df dy is equal to this, right? So let's do that. So df dy is going to be 0 plus 3x plus g prime of y. Right, so we took this derivative with respect to y because we had some arbitrary function of y, and then we're going to compare it to this guy right here, which is also df dy. So 3x plus 2y. So then we can see that we have 3x in common, so then we know that g prime of y has to be 2y. And then if we want to find g of y, when we integrate gy, we get, we get g of y is equal to y squared. Okay. And then now we can add plus some c. Okay. So in general, our solution, fx comma y, which is a function of x and y, we go back to this, and we just throw this in instead of g of y. So we get x squared plus 3yx plus y squared plus c. So this is your answer, and it's not exactly your answer because we have an initial condition, so we gotta do a little bit more. I almost jumped the gun here. Okay, so what we could do is, okay, so fx comma y, we usually have this whole fx comma y is equal to 0. So 0 is equal to x squared plus 3yx plus y squared. And I'm going to say k. So k is our new constant. K is minus c. Okay, now I'm going to input these values. So all the x's are going to be zeros and all the y's are going to be 2's. So 0 plus 4 is equal to k. K is equal to 4. So then I could write my solution as x squared plus 3yx plus y squared is equal to 4. That's my solution to the differential equation. And if you wanted to write it as the function x comma y, like this, what you could also do is you could write it as f(x comma y) is equal to x squared plus 3yx plus y squared, and then minus 4. It's the same thing, just two different ways of expressing your solution. Okay, so let's try to solve this differential equation again, and hint, it's going to be an exact differential equation. Okay, nonetheless, 2x e to the 2y, and then we'll write this as dy, and then we're going to multiply the other side by dx, 3x4 plus e to the 2y dx. Okay. There we go. They're loaded in finally. Okay, and then I want this to be in the form that I usually like it, so I'm going to get this side and subtract it here. So I'm going to have 3x to the 4th plus e to y dx minus 2x e to y dy. And this is all equal to 0 now. Okay, so then we could see that this is m, and including the negative is n. So if we take dm dy, what do we get? We get 2e, no, we get 2e 2y. Then if we take dn dx, what do we get? We get negative 2e 2y. So they're slightly off. Great. We got to use a formula. Formula goes, I'll write in green, is we go m with respect to y minus n with respect to x divided by n, and we'll call this u. And then where we go n with respect to x minus m with respect to y divided by m, and we'll call this u2. And then what we do is we either go like this, u, and I'll write u du, but it's really going to be u as a function of x or y. I'm just writing u du just for the sake of this. And then we multiply dE. And that's our integrating factor. That's how we can actually start doing our work. Okay, so nonetheless, let's go on. And let's see. Okay, so what should we use? Maybe we should use this one. Why not? The reason why I want to use this one is because look. Oh, let's use this one actually. Sorry, I was looking at the wrong equation. So the reason why I want to use this one is because when we divide by this, it'll be really nice and easy. At least hopefully. So m with respect to y is right here. So we write 2e to the 2y, and then we're going to minus n with respect to x. So it's going to be minus minus, so this can turn into positive, 2e to y. Then we're going to divide by n, and n is right here, which is negative 2x e to y. And as you can see, what do we have? We have 4e 2y divided by negative 2x e 2y. And these e's 2y's can go away, so we're just left with negative 2 over x. Okay, and then we want to take the integration of this, but as an exponential. So real quick, I'm going to just... So now we want e to the negative 2, 1 over x dx. And this will become, this is going to equal to, e to the negative 2 ln x. Okay, sorry, I didn't want to skip a step there. God, my nose is itchy. Okay, so now we get e to the negative 2 ln x is the same thing as e to the ln x to the negative 2. And then we can drop the e and the ln and just write this as 1 over x squared. So now if we multiply this, if we multiply our differential equation right here, all by 1 over x squared, so I'll do it. So we go, wait, 3x to the 4th plus e to the 2y dx. Oh my god, my nose is so itchy. Dx minus 2x e to the 2y dy equals to 0. If we multiply everything by 1 over x squared, what do we get? We get an equation that we can actually use the exact formula, or the exact method I like to say. We get 3x squared plus e to the 2y over, great, my tablet timed out, divided by x squared dx, then minus, and we're going to get 2 over x e to the 2y dy. Okay, so this is what we get. And now we can actually do our whole exact method, but before we do that, I'm going to try to make some more space. Okay, so again, we're going to repeat the process. So dm, dx, and yes, you know by now that this is m, so we're going to take this with respect, not to dx, with respect to dy. What are we going to get? We're going to get 2 e to the 2y divided by x squared. Okay, and then we're going to take dn dy, dn dx. Taking this with respect to x, what do we get? We're going to get negative 2, and then since there's x to the negative 1 here, this is like x to the negative 1, it'll be negative negative, and then it'll be 1 over x squared e to the 2y. And as you guys can see, these are exactly equal. So yes, we can go about our whole thing. So now we can write, we'll pick a side, we'll pick maybe this side, why not? And so we'll go dn dx, we'll go, this is what? This is n, and we said n is equal to df dy. So then when we want f, we go n dy. So what is this going to be? Okay, so we're going to integrate n. This is n, so negative 2 over x e to the 2y dy. And look at this. This just becomes negative 1 over x e to the 2y, because the 2 will go on the bottom and we'll cancel out that 2. But then we do have some constant g of x. So if we take this derivative, I know it's kind of like funny, we take an integral and we take a derivative right after, right? If we go df dx, because we want to find out what g of x is, then we get negative 1 over x squared e to the 2y, right? If we take this derivative, it becomes, this will actually become a positive 1 over x squared plus g prime of x. And we know that this is exactly equal to this guy over here. So we get that this is equal to 3x squared plus e to the 2y x squared. So as you can see that we have this and this is the same. So then we know that g prime of x is just 3x squared. So we know that if we take the antiderivative of g prime of x, we see that g of x is equal to the antiderivative of 3x squared dx, which is going to be 3 over 3 x to the 3, right? Plus c, which is just x cubed plus c. Okay, so if all that is true, now we can go back and then we could write fx comma y as this guy plus this. So it'll be negative 1 over x e to the 2y plus x to the 3 plus c. And this is your final answer. There you go. Oh, damn it. So the integrating factor is what kind of slowed everything down, and me itching my nose every 3 seconds. Okay, this is going to be your first linear differential equation that we'll solve in this video. Let's go about it. Okay, so we'll just start off by identifying the integrating factor, which is right here. We'll be using this to find our integrating factor. I'll say mu of x is our integrating factor, which is negative 2y dx. So whatever, even if it's a function of x, everything here in front of this y, including the negative, you put it right here, and then you integrate it. This is e to the negative 2x. Okay, there you go. That's your integrating factor. And then this is the formula. You literally go y mu of x is equal to the integral mu of x, and then you call this f of x dx. And again, I'll write out the general formula for mu of x. Mu of x is equal to e to the p of x dx. And then we know that our equation, our general differential equation, is in the form y prime plus p of x y equals f of x. That's the standard form. So all of this you instantly get. I really like first order linear differential equations because they're really simple and they don't try to confuse you. So we'll just plug in these numbers, plug in these functions. By the way, you cannot like divide this one out and like cancel this. That's not how it works. Once there's the integral sign and there's a function of x here, it has to stay. I wish it was the other way. 3e to the 2x dx. So you can see the e to the 2x's cancel out, and then we just get 3 dx, which is 3x plus c. So then your answer is going to be y is equal to e to the 2x 3x plus c. If you divide by this, it becomes a positive when you divide it. And there you go, that's your answer, just like that. Okay, and you're going to notice that this equation is very similar to the last equation, except this one has this. Oh, damn it. I do not want to do that. Has this. So the general form of this is going to be y prime plus p of x. Y is equal to y of some degree n times f of x. So the way we can do this is the Bernoulli equation is we make a substitution. We go u is equal to y, 1 minus n. So in our case, it's going to be, what is that? It's going to be y. This is going to be 1 minus 2. 1 minus 2 is negative 1, which is 1 over y. So we said that u is equal to 1 over y. And then we could also say the other way around, that y is equal to 1 over u. Specifically, we want to use this relationship to replace everything in here, right? All the y's with u's, basically. So if we take dy dx, that means we're taking the derivative of this as well. So we'll go, that'll be negative 1 over u squared, and then this will be du dx, because there's a chain rule, because y is a function of u. So if you take the derivative of y, then you're taking the derivative of u, and if you're taking the derivative of u, then since y is also a function of x, then u is a function of x. Okay, sorry, that's a lot of words. So you can use this, swap it in there. So the dE becomes now negative 1 over u squared, du dx. Minus y, what is minus y? It's going to be minus this. And then this will be equal to e to the x. And then y squared is going to be 1 over u squared. Okay, there we go. And obviously this is kind of ugly like this, so we want to make it go back to this form. We don't want to look something like that. So what we do is we try to get du dx by itself. So if we times everything by this, right, to make it look like a little bit nicer and solvable, we get du dx is going to equal to minus 1 over u. Then we go u squared over negative 1 is equal to e to the x. 1 over u squared times u squared over negative 1. And then you can see that what do we get? We get du dx is equal to 1 is equal to positive u, which is equal to negative e to the x. Okay, now that looks a lot easier to solve, and now we can do our integrating factor. So we'll go mu, not u, it's mu. Mu of x is equal to the antiderivative, e to the antiderivative of whatever this is. It's only a 1 here, so it's 1 dx, which is e to the x, and then we can go and use this. So usually we write y mu of x equals f of x mu of x dx. For us, what we're going to do is we're going to go u mu of x is equal to f of x mu of x dx. So it's just a change, just one little change. Okay. So if we use that formula, and then, okay, so u, just write u as u, mu of x is e to the x, and this is equal to e to the x times, what is f of x? F of x is e to the x dx. There we go. Oh, this is our, what's it called, f of x in this case, by the way, my bad. So this should be times negative e to the x dx. It's important to recognize that you're using this differential equation and its components into this formula. You're not, this formula goes with this stuff, right? For like a regular equation. This, you're going to use this Bernoulli form and use this Bernoulli form for that. Okay. So then we get negative e to the 2x dx, which is equal to what? E to 2x divided by 2 plus c. Okay, so then u is equal to what? We want u by itself, so we're going to divide everything by e to the negative x. So we go we're going to divide everything by e to the x. So this will be e to the 2x divided by 2 plus c, and then you can rewrite this as what? You can write this as negative e to the x divided by 2 plus c e to the negative x. That's another way you can write it. And then you know that u is 1 over y. So what you can do is you can take the reciprocal of everything. So you want y, and that's going to be 1 over, my bad, e to the x over 2 minus plus c e to the negative x. And you guys can see that we can do a little bit of this and write it a little bit nicer. So e to the negative x divided by 2, if we divide the other side by 2 and times by 2, we'll get e to the x plus 2c e to the negative x divided by 2. And then we can write this as 2, and I'm going to write 2c e to the negative x minus e to the x. And then if you really want, you could write this as 2k e to the negative x minus e to the x. And then that's like the nicest looking answer that you can get, really. There you go. That's your answer. Okay, I almost forgot to go over homogeneous equations. Okay. So, you know, there's the usual substitution where you go like y equals ux. And you go like that. Now, by the way, first off, to do these substitutions, you gotta make sure that, like, you can. So, when you say it's homogeneous, everything would be of the same degree, right? Like, this is polynomial 1, polynomial 1, polynomial 1, polynomial 1. 1 divided by 1 is 1. So they work. Each term has to have the same degree. Now, we're not going to use this substitution. We'll be using this substitution, u equals y over x. And for the most part, you can make any sort of substitution, really, to fit your case, as long as it's homogeneous and your substitution makes sense. For this one, this will make a lot of sense. So we'll go u equals y over x. So then we're going to replace this stuff. But before we do that, let's go write this as y is equal to ux. Now the reason why I went back to this is because I want to find dy this way. Dy, if we take dy dx, then we get u. Actually, the easiest trick is I just remember this. Dy is equal to u dx plus x du. And then we divide, we get dy dx is equal to u plus x du dx. Okay, so we're going to use this guy, insert it over here, and then we're going to use this, insert it over here and here. So you'll notice in a second, we're going to get our d is going to look like this. U plus x du dx is equal to e to the u plus u. Okay, and now this looks a lot nicer. We can minus out those u's. And look at this, it's a separable, so we see x du dx is just equal to eu. And then separation of variables, what we can do is we can put dx on the other side and divide eu on the other side. So we get x du is equal to eu. And then we get dx. And let's divide by that x now. We can write it on the side. There we go. Sorry, that looked kind of ugly for a second. Nonetheless, we can integrate both sides. So we have e to the negative u du is equal to the integration of x, 1 over x dx. So then we know that this is going to be negative e to the negative u, and it's equal to, damn it, my tablet timed out again, which is equal to ln of x plus c. Okay, so why don't we just write out, make this look a little bit nicer. So we'll just take this portion, and then we're going to go EU is equal to what is going to be C minus, it'll be negative ln x plus C, which is the same thing as, we'll write it as ln 1 over x minus, we'll go plus k. Right, it's plus k, so we're just changing the constant, which is totally doable. And then e to the u, we want to get rid of this, so we can write this as ln e to the u, which is equal to ln of ln 1 over x plus k. And then the e to the u, we can just write this is now just u. But then what is u? U is equal to y over x. So a lot of equating here I'm doing. Nonetheless, we want y is equal to x ln of ln 1 over x plus k. And this is your answer right here. This is the nicest way it can look, in my opinion. Okay, higher order equations now. Let's just keep them homogeneous. This will be the first example we'll do. And we'll go to undetermined coefficients and variation of parameters later. Okay, nonetheless, we represent this with the characteristic polynomial 3m squared plus 4m. Great, my screen's not recording. Okay, then minus 3 is equal to 0. So what we want to do is represent this differential equation as a polynomial. We call that the auxiliary or the characteristic equation, whatever you want to call it, that's fine. So that's how we do it. And then we want to find the roots of this polynomial. So I'm just going to jump to the quadratic formula because I like formulas because they're easy. So I'll write out the quadratic formula if you don't remember. Okay. So negative b, this is b, so it's going to be negative 4 plus or minus. Then b squared. B squared is 4 squared, which is 16. And then AC, so it's going to be 3 times negative 3, which is negative 9. And negative 9 times negative 4 is negative 36. Negative 9 times negative 4 is positive 36. And then divided by 2a, a is 3. Okay, so we'll simplify this over here. We get negative 4 plus or minus 16 plus 36. That's going to be 40 plus 12. 40 plus 12 is 52. 52 over 6. Instead of writing it as 52, I'm going to write it as 2 times 26. Instead of writing it as 2 times 26, I'm going to write it as 4 times 13. Okay, you'll see why in a second. So this is going to be equal to negative 2 over 3 plus or minus. Then I could write it as 2 over 6, 13, which is equal to negative 2 over 3 plus or minus 13 over 3. There we go. Okay, and then we can write our solution as y is equal to c1 e to the, now this will have a positive and a negative value. So a positive value will be negative 2 plus square root 13 all over 3. The negative one will be negative 2 minus square root 13 all over 3. So, damn it, my screen. Okay, there we go. I had a problem like that earlier. So this will be, we'll put the positive one here, and then we'll do the second one later. It'll be e to the negative 2 plus 13. I should write that negative 2 a little bit more attached to it. All over 3 plus c2 e to the negative 2 minus square root 13 over 2. So that's your answer. Oh, don't forget your x, right? Because remember the form is y equals c1 e to the root then times x. That's the form. So here's our answer to our differential equation. Yeah, this is kind of like the ugliest it looks. Yeah, to solve this differential equation, we're going to use two methods. We're going to use the method of undetermined coefficients, and we're going to use variation of parameters. Let's start using method of undetermined coefficients. Okay, so save space, I'm going to start writing here. M squared minus m is equal to 0. And we could see this as m is equal to m minus 1 is equal to 0. Then we could see that m is equal to 0 and m is equal to 1. Those are the two roots. Okay, so if that's true, then we can write our complementary solution. yc is equal to c1 plus c2 e to the x. Okay, so that's nice. Well, we need to describe the right-hand side. So the right-hand side is equal to e to the x. We can model its solution as yp is equal to a e to the x. However, we ask this question, is this similar to this? And yes, it is. They're identical. They are copies, right? They could be duplicates. So to account for that, we cross this out, and we say yp is actually going to be equal to ax e to the x. So you times it by x to account for that multiplicity here, the hidden multiplicity. Okay, so you can use this. You can use this and find y prime of p and get a x e to the x plus a e to the x. And I'm going to simplify this a little bit, or write it a little bit nicer. That's e to the x ax plus a. Yeah. I'm tired. And then now we could do y double prime of p. And it's going to be, we'll use this. So the e to the x, ax plus a, and plus e to the x, a. Okay. And again, we'll simplify this a little bit. Right, this is e to the x and ax plus 2a. Okay. So now we can use this stuff to recreate our dE. So this guy minus this guy, it's going to be e to the x. I'm going to factor out e to the x from both of them. Ax plus 2a. And then it's going to be minus this because the differential equation says so. Minus ax. And then minus a. And all this is equal to e to the x. As you can see, ax and ax go away, and we just get e to the x. A is equal to e to the x. We know a is equal to 1. There we go. So that's pretty useful. Okay. So then you can say that y p is actually going to be, so a is equal to 1, so we're going to insert 1 here. It's x e to the x. Okay, with that said, then we can see that y is equal to yc plus yp, which is equal to c1 plus c2 e to the x plus x e to the x. So we want the same answer when we use variation parameters. Okay. Now I'm going to write down the formula for variation parameters. Specifically, we go like, we do this, we say the Run-Skin is equal to y1, y prime 1, y2, y prime 2. And then we say that we have yp which is equal to negative y1 u1 plus y2 u2. And then on top of that, then we say that u1 is equal to, what do we say it's equal to? We say it is equal to f and y2 divided by w dx. And we also say that u2 is equal to f y1 w dx. We use these facts. And by the way, this, I should have said it earlier, right? That y1 is, it's going to be, you get y1 and y2 from this complementary solution. So remember there's like a 1 here, so y1 is 1, and then c2, like you can ignore the constants, then y2 would be e to the x. And so this would be 1 e to the x, and you take their derivatives, which is 1 e to the x. And then the way this works is you go that minus that. It's e to the x. Who would have guessed? Okay, so then you could now say that u1, and remember f is this, so it'd be e to the x times e to the x, because that's y2, all divided by e to the x dx, which is e to the x dx, which is e to the x. u2 is going to be the integral. It's going to be e to the x, and then what is y1? y1 is 1. Once again is e to the x dx, which is going to be e to the x dx. Right, my bad, the screen is not copying. There we go. ex cancels, so it's just going to be x. And I'm choosing my constants to be 0 here in this case because I can. That's just how the math works in this case. Okay, so that's u1, u2. So then negative y1 times u1 is going to be negative e to the x. u2, we get y2, u2. y2 is e to the x times x. Okay. So you see that yp is, it's going to be x e to the x minus e to the x. Alright, and then you add this to yc, and you still have the same yc, which is c1 plus c2 e to the x. So when you add them together, yc plus yp, what do you get? Well, you would see that we get c1 plus, and all the e to the x's, I can do this, e to the x, c2 plus x minus 1. And that's your solution. There we go. And before, sorry, I didn't mention this, I should have said, yes, this is the same answer as this. Let me just show you why. C2 minus 1. What can we call that? We can call that C3, or you can call it another variable if you want. Now you can write y is equal to C1 plus e to the x. It'll be k plus x. And then we could write this kind of similarly if we want to. C1 plus k e to the x. Damn, my tablet timed out again. Plus x e to the x. And doesn't that look exactly the same now? Should have mentioned that. It was almost stopped without mentioning that. See, look. A lot of times C2, like C2 is a constant minus a constant, you can write as another constant. Just a little bit of a algebra trick. Okay, and this will be the last problem we do. This is going to be a Laplace problem. Now, we'll use Laplace's method. Now, solving delta dirac problems are kind of similar, like solving unit step functions in all Laplace problems, because we always use this table, so that's why there will only be one of these. On my channel, I have a lot of other problems, different problems, but for the sake of this review, I want to keep it short and just one for one. Okay, well, let's just continue. We take the Laplace of this, of y prime minus 3y, and the Laplace of the delta function, t minus 2. And then we could see that the Laplace of y prime minus 3y is going to be equal to s big Y minus y of 0, and then minus 3 big Y. And we can insert our initial condition, which is just going to be s big Y minus 3 big Y. And if we factor out the big Y, it is just s minus 3, which would represent the characteristic polynomial equation. Okay, so here we go. And then let's think about the Laplace of the delta function, delta t minus 2. Well, if we look at our table, delta, 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 here it is. Here's delta. It's just e to the negative cs. So for us, it's going to be e to the negative 2s. E to the negative 2s. Okay, so now we can write everything as big Y, s minus 3 is equal to e to the negative 2s. Make it look a little bit more like a negative 2s. And then if we want big Y by itself, like we do, we say big Y is equal to e to the negative 2s divided by s minus 3. And we want to take the inverse of this, so y, because that's our solution, the inverse of e to the negative 2s divided by s minus 3. And then we could see that if we have this, right, we go back, and if we're taking the inverse of e to the negative 2s, which, where is it? Right here. We're taking the inverse. Right, here's the thing we got. We got some function s, and then we have e to the negative s. Let's see, let me find it. Right here. Here it is. So if we got e to the negative 2s, and then f of s is 1 divided by s minus 3, we're going to go to this. We're going to jump to the unit step. I'll explain it a little bit better in a second. So we have Laplace inverse of e to the cs, and then some big function f of s. And big f of s is what? It is going to be 1 s minus 3. And then we say that this is equal to, we'll go back to it. Where is it? Right here? uct ft minus c. Where is this? Yeah. So it's going to be uc ft c. And by the way, uc is the same thing as u of t minus c. It's just the shorthand notation. Okay, so we're going to use all that, but first let's find f of t. So f of t is equal to the inverse Laplace of f of s. And for us, that's the inverse Laplace of 1 over s minus 3, which is e to the 3t. And let me just check my table if I got that correct. Damn it. Yeah, see, this is the formula. For us, it would be e to the 3t. Okay. So, that's f of t, but we want f of t minus what? Minus 2. So we'll have e to the 3, it'll be t minus 2. And you can leave it like that. And then u of c, for us, is going to be u of t minus 2. So our answer is y is equal to u of t minus 2 multiplied by e to the 3 t minus 2. So there you go. That is your answer to the differential equation.
Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up the algorithm.